He kindly agreed to speak on this conference because, as I remember very well, for many years, Alan and Ludwig Dmitrievich were close friends. Thank you, Alan, for agreeing, and start.
Okay, it's a great pleasure and honor for me to give this talk in the conference for Ludwig Faddeev, who was really, a great physicist and a great mathematician, and also, a very good friend of mine. And I remember vividly when I came in the same place, St. Petersburg, when Ludwig was, in his seminar. And instead of sitting, he was, going from one row to another, explaining things to the participants of the seminar. So he was such a tremendous scientist that for me, it's really a great honor. So what I will do is, I hope you will understand the title of my talk, and I will give you a partial answer. So the title of the talk is, Can One Hear the Shape of the Archimedean Prime? So I will have to explain what the Archimedean prime is. And but I don't think I have to explain much about can one hear the shape, because this is a very familiar title, which is, due to Mark Katz, which was Can One Hear the Shape of a Drum? And the reason, of course, is something well known, but it is the fact that when you have a shape, okay, like a drum, for instance, then you have a corresponding spectrum, and somehow this spectrum, is intimately related to the shape in the sense that it's an invariant of the shape. It's a fundamental invariant of the shape, but somehow this invariant is not necessarily a complete invariant. Namely, you can have shapes which have the same invariant, but which are not isometric to each other. The first example of such shapes was given a long time ago by John Milnor in the paper, which is probably the shortest paper of all in mathematics. It's a paper which has one page, and in which John Milnor was giving two tori of 16 dimensions, which were isospectral, but which were, of course, which were not isometric. Now, so what happens when you have a shape of 2 dimensions, like a drum, is that the heat expansion, if you want the expansion of the trace of the exponential of minus t delta, where delta is a positive Laplacian, gives you some information. It gives you an information about the area. It gives you an information about the length of the boundary. And it also gives you an information about the number of holes. Okay. So if you want, there are plenty of examples where this type of computation has been done. It has been done for closed manifolds of dimension n. And in that case, when dimension is n, there is an inverse power of t, which is n over 2. And then there are other terms. In general, these terms are very hard to compute. And in fact, there are very few examples where all the terms of the expansion can actually be computed. Now, very recently, I did a computation, which is a computation which has to do with a space which is handed to us not as a space, but by its spectrum. So if you want, it's a very, very mysterious shape in the sense that the way it manifests itself so far is by its spectrum. And this spectrum looks like this. So this spectrum has this following form. The first element in the spectrum is like around 14. Then it continues like that. And you probably have recognized here the non-trivial zeros of the Riemann zeta function, which I put with their imaginary parts here. Okay. Now, of course, when you see this, it's extremely tempting, and this has been discussed so many times. It's extremely tempting to say that, after all, this has to be, the spectrum of a Dirac operator. The reason why it should be a Dirac operator is that you have this symmetry between the plus part of the spectrum and the negative part of the spectrum. And then, of course, I mean, you know, there is an obvious question, which is, well, if it is the spectrum of a Dirac operator, can we guess the shape of the corresponding space? Now, the computation which I did very recently, I had never sort of applied myself to do it in full. It's a surprising computation because the claim that I make is that one can compute the heat expansion of this putative operator. And when you do the putative expansion of this operator, if you want, what you find, amazingly, you find that you can compute all the terms, not only the first terms, as it would be, okay, in the case of a drum or something like that, but you can actually compute all terms. So I did this computation. Of course, for the computation, you assume RH, but I mean, this is not really the important point. And so you take a self-adjoint operator whose spectrum is formed by the imaginary parts of these non-trivial zeros of the Riemann zeta function. And then what you find that by doing some work, which I will explain, you can take the trace of the exponential of minus t d squared, where d is this operator, and you find a very strange formula. You find that the first term, so the first term, if you compare with what it should be in dimension 1, tells you that it is not, I mean, it's dimension 1, but it's of infinite length, because there is this logarithmic divergency in front. So if it were not, if it were of finite length, there would be a constant in front of the 1 over square root of t. Here it's divergent. So there is this log of 1 over t. Then you have this term. This term is, of course, very tricky because you have log of 4 pi. Okay, this is not too bad. But this is 1/2 of the Euler constant. So this already tells you that you are really in deep waters because you have the Euler constant in the expansion. Okay, and then you can actually compute all the terms in the expansion. These terms, okay, there is this one which is too easy to write. But then the terms that you get here, these AN, they are either coming from Bernoulli numbers or from Euler numbers. So the AN for n is odd. They are really coming from the Bernoulli numbers. And the AN for the even values of n, they are coming from Euler numbers. I will tell you what are the Euler numbers very shortly. What is important, what is really, really important is that this is only an asymptotic series. In other words, this AN behave really like factorials. So this series is not convergent at all. It's typical of the asymptotic expansions that you get when you do geometry. Okay, so this is where we are. And so, I mean, to be more specific, the Bernoulli numbers are, of course, you know, very well-known coefficients of the Taylor expansion of this function. And the Euler numbers are a variant. They are obtained when you look at the Taylor expansion of this function here, okay? And they are known, of course, to satisfy remarkable arithmetic identities. For instance, the even zeta values, this is the origin of the Bernoulli numbers, are given by this formula, as was known to Euler. And the other ones, I mean, the Euler numbers, they are related in the same way to the evaluation of a function, which is the Dirichlet beta function. It's a variant of the zeta function because you put a -1 to the end, so you have a nice convergence, and you have this, okay, there should be a z, okay. Okay, so now how does one prove this, how does one effect the computation which I just showed you? Well, it's done by using the Riemann-Weil explicit formula. I mean, it's called Riemann-Weil. I mean, in fact, it was Guinan who did part of it. The name of Riemann should be there, of course, because he knew this formula in some way or another. And then André Weil reformulated it in a way which is very nice. Now, so this formula is the following. It shows you, if you want, a kind of duality between the zeros of the Riemann zeta function. So this is the set Z of zeros of the Riemann zeta function, and the primes. But what you find out is that it's not enough to take just the ordinary primes. You still have to add another prime, and this is the infinite prime I was talking about in my title. So in other words, you see, when you write the Riemann zeta function, for instance, as an infinite Euler product over all the primes, well, that function is not ideal because it does not fulfill the functional equation. And you have to add a contribution of the infinite prime, which is essentially a gamma function. And that means that when you want to have a duality, this duality will involve a sum of terms here. And these terms are parameterized by what mathematicians call the places of the field of rational numbers. Now, these places are the ordinary primes, but also the infinite prime, or if you want, what mathematicians call the Archimedean place. The point of a place is simply to be a completion of the field of rational numbers, which is a local field. So you can do that by p-adic numbers, but you can also do that, of course, by real numbers. And this is the real place, or the Archimedean place, or the infinite prime. And these contributions are explicitly computable. They are computed. The contribution of a prime is quite simple. It's given for each prime p by log p, which is in fact the length of a periodic orbit, times the sum of the evaluation of the function on the powers of the prime. Okay. But the contribution of the Archimedean prime is as follows. It's tricky in the sense that you have this log of 4 pi. Here, notice that you don't have 1/2 of gamma. You have gamma, which is, so it's different from the formula, which I showed you before. And then there is a distribution, which is tricky because it's a Hadamard principal value in the sense that what you have in the formula for the distribution is divergent for x equals 1. And so you have to take a Hadamard principal value by removing this quantity, the value of the function f at 1. So you do that. But the remarkable fact that comes out of the computation is that in the heat expansion, which I showed you before, these primes do not contribute. And the reason why they do not contribute is that in this formula, the test function f is evaluated away from 1, and so it does not contribute to the asymptotic expansion. I mean, I don't know the exact analogy with physics, but it's a little bit like something which would not contribute to the, if you want, to the high energy expansion, and which would be totally outside the asymptotic regime. So that's what you have. And this explains the statement of my title, because what we have available when we have this asymptotic expansion, okay, the one I was showing before. So what we have available in this asymptotic expansion is really coming only from the infinite prime, from the Archimedean prime. It's not coming from the ordinary primes. So in other words, when you look for this operator, you find out that, okay, of course, I mean, if you really want to get exactly the zeros of the Riemann zeta function, you will have to involve the primes. However, if you want to have this kind of ultraviolet behavior, if you want, with all the properties of the ultraviolet behavior, which are given by the asymptotic expansion of the heat kernel, no, the primes are not involved. So in a way, what it means is that this asymptotic expansion is giving us, if you want, the music of the Archimedean place. And the challenge that I'm going to address, and which is a joint work with Henri Moscovici, is to find a space, a geometric space, which reproduces this. And what we did with my collaborator, so with Henri Moscovici, and this is, if you want, the main topic of my talk. So I will come back to that just in a moment. But so what we did with Henri Moscovici is to find such a space. And the way we found it is by accident. I mean, we were by no means looking for something that would reproduce this asymptotic expansion or anything like that. We found it by accident. I will explain how this accident occurred. But it was not, you know, if we had to write, for instance, a proposal, NSF proposal, and so on, to explain what we wanted to do, I mean, never we would have been close to the result that we have obtained. So, I mean, I should mention that there is a way to relate the first terms of the expansion, which are the interesting terms, if you want, these terms, which are really, really very surprising. I mean, this term, which is telling us that it's dimension 1, but it's infinite length, and this term here. So, I mean, these terms are exactly related to what Riemann wrote in his paper, which is that the number of non-trivial zeros of imaginary part between 0 and E as an expansion, and that this expansion is given by this formula E over 2 pi times log of E over 2 pi minus E over 2 pi plus the terms in log E. The reason is quite simple. Imagine that you were looking for a one-dimensional manifold, compact torus. Then, of course, the number of eigenvalues, which are between 0 and E, for the spectrum of the Dirac operator, would just be E, proportional to E. Here, as you see, there is this log divergency. So the fact that there is this log divergency is exactly the same corresponding to this term. Okay, and so one can plot, one can compare with the calculation. I mean, with now, of course, with the computers, we have access to many, many zeros of zeta, so one can compare the asymptotic expansion, which I gave you, together with the actual expansion, and they match exactly. Okay, so now let me explain this. So in fact, a long time ago in 1996, and in fact in a paper in 98, I had used the Prolate wave operator. I had used the Prolate wave operator to construct a cutoff which was necessary in order to compare my spectral realization of zeros with the, with the, if you want, the exact formula. And in order to make a cutoff, I was considering, in fact, two projections in the Hilbert space of even functions on the line. So you consider L2 functions on the line, you consider which are even, and now for each lambda, you consider the projection which is exactly coming from a cutoff, namely you take functions which are vanishing outside the interval minus lambda lambda. Okay. Now, this is a projection, perfectly fine. Of course, it's infinite dimensional and so on, and it corresponds to localized functions. Now, it turned out that for what I was doing, one was also needing another projection, which is Fourier conjugates of this projection P lambda. So in other words, what one is trying to do is trying to localize the function in space and to localize it in momentum space. So one is trying, if you want, to find a function which is localized between minus lambda and lambda in space and also in Fourier transform. Of course, this is not possible because if you have a function f which is localized between, which has compact support between minus lambda and lambda, its Fourier transform is an analytic function and it cannot be localized. Okay. But what turns out to be the case is that when you have a pair of projections in Hilbert space, this situation is perfectly understandable because it's equivalent to giving a representation of the diedral group. The reason is that when you have a pair of projections, it's the same thing as having a pair of self-adjoint unitary operators, namely unitary operators which satisfy u square equals 1 and v square equals 1. Now, when you consider the group generated by two elements of square 1, u square is 1 and v square is 1, this group is a very, very nice group. It's called the diedral group. The point is that you can form words like UV, 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 U, or words of this type, but these words are just a power of UV preceded by a V or not. So what you have is a semi-direct product of the group of integers by the automorphism, which is changing an element to its inverse. And this group has a representation theory which is quite easy to get, which is by the Mackie theory. Mackie theory is telling you that the reducible representations of this group are two-dimensional, and they are classified by an angle. So in fact, when you have a pair of projections in Hilbert space, they are entirely classified by their angle. This angle is an operator, and the eigenvalues of this angle give you the values, if you want, of the parameter which parameterize the irreducible representation. So all of this situation is perfectly understood. And for this pair of projections, a long time ago, in the 60s, a miracle occurred. And this miracle is due to physicists who were also engineers. They were working in Bell Lab. And what these physicists were doing, they were trying to optimize communication. And when you try to optimize communication, you find yourself exactly in the same problem. Why? Because you see, imagine that my R here is time. So I am giving my talk. My talk has a limited length. So I am with compact support. I am between two bounds, okay? Now my voice has also a limit in Fourier. So I am also limited in Fourier transform. So this seems contradictory. And I mean, what Slepian and his collaborators, Landau and Pollack, did was to tackle this problem, to try really to completely understand this pair of projections. And the miracle which occurred is, I mean, in their various papers, in the papers which they wrote, and the miracle which happened is the following. It turned out that one can actually diagonalize this pair of projections, because what happens is that they commute with a certain differential operator. So their discovery is that this pair of projections actually commute with a second order differential operator on the line. And this second order differential operator was known before. It is called the Prolate spheroidal wave operator. And I will explain what it is concretely. So this operator, so what is the Prolate spheroidal? Well, it's like a rugby ball, okay? So I mean, it is a solid body. It's not a, I'm not talking about the boundary, I'm talking about the inside. So it's a solid body, three-dimensional, and it has, of course, rotational symmetry. So it has this axis of symmetry, and it's ellipsoidal. Now, when you want to compute the Laplacian for this spheroidal, this Prolate spheroidal, you have to, you can use actually some coordinates which are called the Prolate coordinates. There is, of course, the angular parameter, but which plays a trivial role. And but the other parameters, what do? They parameterize confocal ellipses, which have a certain focal distances, and these ellipses look like that. They all have the same foci, F plus and F minus, and they form, if you want, a family of such ellipses which have the same F plus and F minus. And then using these coordinates, you can actually show that the Laplacian for the solid body occurs with separation of variables. So what you have is that, especially when you consider the rotation invariant solutions, where namely the solutions which do not depend on the angular parameter, then what you find out that in fact there is two occurrences of the same operator, and this operator is a Prolate spheroidal operator. And so, I mean, now it's an operator which is dealing with functions of one variable. It depends on a parameter, lambda, and it has the following form. This operator is, if you want, it's second order, and it has a mix of two terms. If you look at it a bit, you will find out that it is really, if you want, the square of scaling, because there is dx, x square, and dx. So it's really pretty much like the square of x dx, and x dx is scaling. And then the other part of it is really the harmonic oscillator, because it's like dx square and then multiplication by x square. So it's really a combo of scaling and the Hermite operator. Okay, the harmonic oscillator. So, I mean, mathematicians call it the Hermite operator. So you have this operator, W lambda, and now the extremely interesting and surprising fact is that this operator actually commutes with a projection. And it will commute with P lambda and P lambda hat. This is very surprising. I mean, at first you get extremely confused because how could it be that a differential operator commute with a function which is discontinuous, which is a characteristic function? Now, if you think about it, this is not so surprising because if you take the scaling operator, which is x divided dx, of course, scaling preserves positivity. So it commutes with the characteristic function of 0 infinity. And so if you go a little further, you will find out that because you have multiplied dx by lambda square minus x square, it will commute with the characteristic function of minus lambda lambda. And in fact, this will continue to hold when you take this combo. Of course, the multiplication by x square will commute with characteristic functions. There is no problem. The problem was to commute with differentiation. That was not obvious at all. So now back in the 1998, in fact, I had analyzed the fact that this operator, W lambda, was, if you want, commuting with P lambda and P lambda hat. But what Slepian and his collaborators had done was to look only at the restriction of the operator to the interval minus lambda lambda, and to look only at the positive eigenvalues. So in fact, what we did with Henri Moscovici was to look at this operator very seriously to understand, if you want, its self-adjoint extensions and so on, and to look then much more closely at its spectrum. So the first thing is that this operator, when you consider its natural domain, which is the Schwarz space, I mean, the space of nice smooth functions with all derivatives of rapid decay, which is the Schwarz space, S of R, then it turns out that this operator is not self-adjoint when you take this domain. It has von Neumann deficiency indices, and these deficiency indices are 4 and 4. So, I mean, they are large. They are equal, so you know that there is some self-adjoint extension, but there is a slew of them because the self-adjoint extension are parameterized by all unitary maps from a 4-dimensional space to a 4-dimensional space. But we single out a unique one, and there is a unique, in fact, self-adjoint extension which commutes with this projection P lambda and P lambda hat. So this really requires some works already. And then with Henri, we considered the spectrum. So in fact, you find that this operator commutes with the Fourier transform, okay, of course, because of course the pair of projection was invariant under Fourier. I mean, you know, it was okay, it was constructed like this. So this operator commutes with Fourier. And now the new fact, which is totally new, I mean, is that now when you consider this operator not on the interval minus lambda, namely not for the positive spectrum, which is where, if you want, the separation of variables was leading you, but when you consider it on the full line with this boundary condition, then you find that this operator has discrete spectrum. And what I will explain is that it is this discrete spectrum, it is the negative part of the discrete spectrum that will actually be related to this shape that we are trying to uncover. So in fact, the boundary conditions that you find is that the eigenfunctions of this operator behave at infinity like a trigonometric function divided by x, okay, when x goes to infinity. And so, I mean, there is this fundamental boundary condition at infinity, which is very tricky. And of course, there is also a boundary condition at the regular singular point of the operator. Of course, the operator by construction, because it has this term, dx times lambda square minus x square times dx, has a singularity, but it's a regular singularity, the singularity at plus or minus lambda. Okay, so once you have this and you know that the operator has discrete spectrum, okay, you do like a good physicist, namely you do the semi-classical approximation. And when you do the semi-classical approximation, you find out that the semi-classical way of writing the operator is like this. It's p square minus lambda square times q square minus lambda square. So to be more precise, the operator is minus 4 pi square times this Hamiltonian plus a constant. Okay. And this Hamiltonian now So this Hamiltonian will rule, if you want, the negative eigenvalues, of course, because you have a minus sign here. So it will be the negative eigenvalues of W lambda that will be ruled by this Hamiltonian. And now what you do is you consider the portion of the phase space, which is such that these two terms are positive. So that Q is larger than lambda, P is larger than lambda, and where the Hamiltonian is less than a constant. Okay. Okay, so you draw the graph, you look at this picture, okay, and this will give you the area that you have to compute, okay, in order to have a first idea of what will be the behavior of the negative eigenvalues of this operator. Okay, and so what you find that this area is in fact given by a Legendre integral. So it's given by a Legendre integral. This Legendre integral can be explicitly computed. And when you begin to expand this Legendre integral in terms of the good parameter, wow, you find the same term as Riemann. In other words, you find that the very rough counting that you were getting from the semi-classical approximation is actually giving you the correct term which was appearing in the Riemann formula, namely E over 2 pi log of E over 2 pi. Okay, then you have correction terms and so on. So you have to be extraordinarily careful. And so what you have in terms of elliptic integrals, you have to use the functions K and E of Legendre. And okay, and then you can do the detailed computation. So, but now you have to do better because, of course, the semi-classical approximation is only giving you some idea of the situation, and I mean, can certainly not give you a proof. So in order to do that, what you do is you do a Liouville transformation to transform your operator into a Schrödinger type operator. So there is a canonical way of doing that. In that case, you have to use hyperbolic cosine and sine. And what you find is that it conjugates the operator with this type of Schrödinger operator, where the potential is a very, very tricky potential because it's neither positive nor negative. So it's a potential which, if you want, is going to plus and minus infinity. And so to handle it is very tricky. And you have to use for that some results, okay, which are about eigenvalue asymptotics for Sturm-Liouville operator with potential having a strong local negative singularity. So this is typical of what we have, okay? And then when you input the potential in the formulas, which are, if you want, classical formulas for the number of eigenvalues which are positive and the number of eigenvalues which are negative, okay? Then you get the formula for this number of eigenvalues that we are computing here. This integral is now much more delicate to compute, okay? It's a type of elliptic integral, but it's much more complicated to compute. But what you find is the following, is that at the level of the Dirac operator, namely at the level of the square root, which you have not found yet, okay, but of course, we shall find it a little bit later. What you find is that the number of eigenvalues, which are between 0 and E, okay, is now exactly the right one, namely it's E over 2 pi times log of E over 2 pi minus E over 2 pi plus a correction in log A. And for that, you have to choose the value of lambda to be square root of 2. I will come back to that. But you find a logarithmic term, and this logarithmic term, in fact, can be compared with, it has the same order of magnitude as the best constant, which is for zeta, for the Riemann zeta in the Prussian form, where when you take zeta, the difference between the value for zeta and the value which is here is in fact also known to be logarithmic with a certain coefficient, which is of the same order as the coefficient that we have here. So that's, that's just a nice coincidence for now. But now, of course, one has to find a kind of square root of this Prolate wave operator. And so then we investigated with Henri Moscovici, we investigated how to find a Dirac operator whose square, okay, whose square would give us the Prolate operator. And for that, we use the old method, which is known as the Darboux method. And then we explore the associated geometry. And this associated geometry will be, if you want, our first look at the Archimedean place. Namely, it has to be refined, but it will be, if you want, our first contact with the way the Riemann zeros tell us that it's looking like. So what is the Darboux method? The Darboux method, when applied here, there is in the Darboux method, there is a potential V of x, and there is also a term, which is, if you want, like the leading symbol. So here it's x squared minus lambda squared, and the potential is this. And when you apply the method, you have to solve a Riccati equation. Namely, if you solve this Riccati equation gives you the value of a potential, W, which is a function, and which will be such that your operator will be unitarily equivalent, not to a square, but to a product of, you take a covariant differential and with a plus W and with a minus W. And delta will be a covariant differential, which is given here. Okay, but first you have to solve this Riccati equation. And it turns out that one can solve this Riccati equation by using solution of the Prolate equation, but with the condition, of course, that it has no zero in the, which is not at all what happens for eigenvalues, because for eigenvalues, you have this sinusoidal boundary condition, which is, if you want, in the LCO condition. So whereas here you want to have no zero. So in fact, the solutions are parameterized by a complex number which is not real. This is where it appears. So, but for each of these solutions, okay, which are parameterized by a complex number, not real, we have a solution of the Riccati equation, and then we have a corresponding Dirac operator. And the important thing about this Dirac operator, now, of course, it's a 2x2 matrix, and it should be like that because the Dirac operator in a one-dimensional space, okay, and so on and so forth. So what you have is a Dirac operator of this form, and it has the main property that when you square this Dirac operator, you obtain an operator which is isospectral to two copies of the Prolate operator. So it's spectrally equivalent, if you want, to W lambda. All right. So then, if you want, the main result that we have obtained is that when you consider, okay, there is a factor of 2, okay, for some reason, but then what you find out is that this Dirac operator has a spectrum which is contained in, it's not just the imaginary zeros, it's not, if you want, the non-trivial zeros, it also has a real spectrum. And the real spectrum has the same behavior, in fact, as, okay, what would expect. So, but what happens is that for the imaginary part, okay, you get exactly the right formula. So I want to insist here because you see, as I say, the Prolate operator doesn't have just negative eigenvalues. It also has positive eigenvalues. So when you take the square root, which is the Dirac operator, we are very much in the Lorentzian situation in which the square of the Dirac is self-adjoint, okay? But it's not a positive operator because you have positive and negative eigenvalues. And this will correspond exactly to what we expect. Okay, so what we have is that this number of non-trivial eigenvalues is in fact equivalent to e over 2 pi times log of e over 2 pi minus 1 plus a logarithmic term. Okay, and now comes the hard work on computer. So the hard work on computer is now, if you want to compute explicitly the spectrum of this Prolate operator for the value of lambda, which is square root of 2, and to compare the results that we obtain with, okay, what, I mean, if you want, the type of ultraviolet behaviors that we expect for the Riemann zeros. Okay, so in order to do that, what you do is you apply the following method. There are two boundary conditions. There is one boundary condition at lambda and one at infinity. And so you solve the equation, the differential equation, at lambda, you extend it to the, if you want, up to 1000, something like that. You solve the differential equation at infinity with a boundary condition, and you extend it the other way to 1000. And what you find, what you look at is whether they agree. Here, obviously, they don't agree. Okay, they don't match. Okay, but here they match up to sign, which is fine, which is perfectly fine, because this means that if you take a minus in front of one, you get the other, so there is no problem. Okay, so now you pick this value, minus 38. Okay, and then you use a computer, and with the computer, what you will find is that when this value is moving, these two graphs slide with respect to each other. And so for the next value, which is minus 93, now, boom, they agree. Okay, they agree. And this means that you have an eigenvalue. And then you keep going, and you find that for minus 150, okay, they agree up to sign. The fact that they agree up to sign is in fact telling you that this eigenfunction will be the opposite of its Fourier transform, whereas here it will be equal to its Fourier transform. Okay, so I mean, these eigenfunctions fulfill some interesting properties. And then, okay, so I mean, you do that. I did that by hand with the computer, actually. I mean, and it took a long time to produce this list. You can imagine what it means, you know, to slide these things and to collect the values. And here are the values that, okay, that I could collect up to this, okay? And then you take what the Dirac operator would give you, and you compare this with the zeros of zeta, okay? And you get the following. And what is very important in this list is that it is the same n. So I'm not choosing my n. My n is the same on both, okay? So you do this for a long list of examples, okay, like this one, for instance, and so on, and you keep going up to this one, okay? And then you plot the graphs. So here I am plotting the nth zero of zeta, and I am plotting the nth eigenvalue of the operator. And when you see only red, you know, it means that the red is hiding the blue. So it's not that, you know, there is no blue. I mean, so this means, okay, they look pretty close. And you keep going like that up to the 60th eigenvalue. And you keep going like that. And I mean, so if you want, then one can get the full confidence that one has grasped the, if you want, the ultraviolet behavior of the spectrum. And as I said when I started, you know, since we know that there is this behavior of the counting function n of e, I explained from the start that the behavior of this counting function n of e was implying the fact that the first two terms in the heat expansion were the same as for zeta. So in other words, now we have found a space. I will explain what this space looks like. We have found a space which, when you look at this heat expansion, it has exactly these two extremely strange terms, to which I can come back. Okay, so it has exactly these. Sorry, this. Yeah, so it has exactly these terms, because you see, so what we had was this type of estimate for the number of eigenvalues. And as I said in this slide, it implies that the heat expansion has exactly this extremely strange term, like with log of 1 over t and with log of 4 pi plus 1/2 of the Euler constant. It's not plus the Euler constant, it's plus 1/2 of the Euler constant over this term here. So in other words, now, okay, what we have with this Dirac type operator in this Lorentz type space, okay, so what we have found a space which has the right spectral property. And of course, now we have to understand this space a little more. And when you look at the metric, because of course, the geometry in that case is governed by a spectral triple in the sense of commutative geometry, and you can compute a metric. And what you find is that the metric in the ordinary sense, it's a metric on a half line, starting at lambda, going up to infinity. And the metric look like this. It is like a dx squared, but with a 1 over alpha of x. And I mean, since I'm giving this talk in a physics context, I want to mention that it's in fact a compactification of a two-dimensional Lorentzian space. Namely, you take a two-dimensional Lorentzian black hole, in fact, with periodic time, and namely the space which has this metric. It is, okay. And what you find out is that when you compactify it with periodic time, you end up exactly with this metric which I have here. And so, of course, I mean, you know, then you can do the change variable and make it smooth. I mean, like one does with black holes and so on. I mean, there is no problem here. And I mean, I just want to finish with a picture. So the picture of this kind of Lorentzian black hole looks like this when I embed it. You can embed it in using elliptic functions. You can actually embed it in Minkowski space R3, and it looks like this with geodesics of this type and so on. And so, I mean, you see, what we have done with this stuff is to have a first look at what the Archimedean place looks like. And it looks extremely, extraordinarily interesting and mysterious. And the next steps are that in some works that I had done with Katia Konsani, we had found how to get the infrared part of the Riemann zeros very, very precisely. We were getting the 32 first zeros, but again, using the Prolate operator. So what is very tantalizing is to combine infrared with ultraviolet. And for that, one has to use a variant of the Prolate wave operator in what we call the semi-local case, namely where you don't just consider the real numbers, but you consider the product with periodic numbers for finitely many primes. Okay. Okay, so I think I will finish my talk here. And I thank you for listening. Thanks a lot.
Thank you. Okay, any questions to Alan from the audience? I have one question and one comment, if I may.
Sure.
This whole story is about the function. What is the real role of ordinary primes?
I cannot hear what he's saying. I cannot hear you. Samson, can you?
What is the role of
I
ordinary
just wanted
primes?
to ask, what is the role of ordinary primes, which are implicit in Riemann hypothesis? Just how can you include the ordinary primes into your picture?
Let me
Is there
explain.
a way to see them?
That's exactly what I wrote here. Find the analog of the Prolate wave operator in the semi-local case. You see, what people don't know is that, in fact, concerning the Riemann hypothesis, it's enough to solve it for finitely many primes at a time. And so in my paper in 1998, I explained that there is a framework, Hilbert space framework, which is called the semi-local framework, for which I proved the trace formula. And I mean, it's enough to deal with finitely many primes. So the way that I expect the primes to be included is that it will be a very tiny sculpture on the previous operator, which will be affected when you replace just the real numbers, as I explained, by putting the product by periodic numbers and then dividing. You have to divide by a discrete group. Okay. And so the idea is that, and in fact, we wrote and we put on archive a paper with two collaborators, Katia Konsani and Henri Moscovici, in which we have begun to do that, namely to extend the Prolate operator in this semi-local setup. And so if you want what is behind it, it uses a lot of the theory of orthogonal polynomials and all that, and Jacobi matrices and all that. But so if you want it's like if the mental picture that emerges for me is like what I have now is like a huge statue, but it's missing a lot of details. But if you want, the overall appearance is there. And when one will make the product by periodic numbers and do it will be a little bit of carving on this thing. And because of what I did with Katia Konsani, which is the infrared situation, I know that there is a chance that if you want this minute carving and so on, will actually provide the right stuff. But okay, you know, this is totally. But however, if you want, what is really important there, I have a general remark to make. I think that the Riemann hypothesis is interesting because of what it suggests and because of what it forces us to discover. And if it forces us to uncover a space which is a priori very mysterious and all that, then it will have achieved its goal. If it were proved by a trivial reasoning, it would be a catastrophe in my mind. I mean, I think it's interesting exactly because it forces us to think and do calculations and uncover things which we didn't expect. And in my work with Henri Moscovici, we didn't expect at all that it would be related to zeta. In fact, Slepian and his collaborators, they knew that they had unveiled something extremely interesting, but they would never have foreseen that it could be related to zeta, to the Riemann zeta function. And when we tried with Henri, when we started looking at the boundary conditions for this Prolate operator, we had no idea at all that it would be related to this. No idea at all. We did the computation of the semi-classical approximation. We found the same term as in Riemann. Oh, then we were really surprised and then really interested. That's all. That's all. And I think this is the best that can occur in mathematics. Not that you write a proposal and you do what you have to do. No. No, you look for something crazy and you find something which is totally unexpected.
Other questions before I ask my question from the audience?
I'd like to ask something.
Yes, please. Yes, please. Can you come close so
Yes,
Alan can hear?
Yeah. And what happens in the case of zeta functions for curves over finite fields, where the Riemann hypothesis is?
Okay, sure.
So
okay.
we have an analog of this.
Okay, so let me explain. You see, when you consider, so first of all, the spectral realization, which I had given, was also working for any global field. And I don't want to enter into that. And that was the motivation, yes. But what you have to understand as a difference between the case of function fields is the following, is that in the case of function fields, the number of zeros that you get is finite. And what is new and what is totally mysterious in the case of number fields is this infinity. And this infinity is coming from the Archimedean places in all cases. That's a totally new ingredient, which has no analog in the case of function fields. So if you want, the input that you can get from the case of function fields is nothing with respect to the depth of the problem, which is coming from the Archimedean places. So, I mean, my talk was entirely focused on the Archimedean place. What can we learn about it? What can we know about it? So, I mean, but on the other hand, okay, I mean, you know, the case of function fields is useful, and I used it when I wrote my paper in '98. I mean, so it's not contradictory if you want, but it's something which is totally original, which is totally new with respect to function fields.
Okay, other questions? If there is a question in the hall there, maybe you can stand up so we can see. On the Zoom questions? Okay, Alan, can you go back and show the Hamiltonian, which was quadratic in p square and q square?
Okay, sure. Yes. Yeah. Oh, this one. Okay. Yeah. Let me see.
P square minus q square times. Yeah. Okay. You see, this is one of those. This is from the list of Hamiltonians, which is quadratic separately in p and in q.
Exactly.
But
yes.
not quadratic in total. Now, those kind of things appear, as you already mentioned, in two-dimensional black holes. Okay.
Yeah,
So
exactly.
the two-dimensional black hole has this property. but this one is little deformation of it, as you wrote. So question is, two-dimensional black hole, Lorentzian one, is dual to Liouville theory in 2 dimensions, and one scalar field which are interacting. In Liouville theory, there are formulas for density of states that people did in whatever known things and so on. And it's there, it is mu times log mu, where mu is a cosmological constant. So it starts mu log mu minus mu, and then it's identical to what you...
It's identical, it's the same time, exactly. It's exactly.
It's the same time. Yeah. And our friend Maxim Kantsevich explained it from matrix models.
Okay,
Maxim, the Maxims.
Yeah. Well, okay. No, I mean, I think this is the interest of giving such a talk. You see what I mean? I mean, the only
you see what is specific, Alan, what is specific in here is that if you write Lagrangian in terms of Q or in terms of P, they will be the same.
Yeah, sure. It's
so
variant.
It's very unique.
It's Fourier invariant.
Very unique. It's very unique when Lagrangian written after Fourier transform is the same Lagrangian.
Exactly, and this is the one story here. It's invariant under Fourier. Yes, exactly.
Right. Yeah. And that has been used. People who worked on two-dimensional black holes. Of course, in two-dimensional black holes there are 2 P's and 2 Q's. But as you said, if you compactify, you get this.
I compactify periodic time, and then it works.
Or you can say just look on zero modes. Just look on a zero modes, okay?
Exactly.
And then the spectrum is given by Bessel functions and so on. But my point is that this mu log mu minus mu plus blah blah is described by Kantsevich's matrix model.
Well, I mean, the depth of the problem is such that, I mean, as I said, one will uncover a lot of things which are totally unexpected.
Just comment, I said.
Yeah, sure. Okay. Thanks a lot.
If there are no other questions, we thank Alan again for the very inspiring lecture. Thank you, Alan.
Thank you.
Bye-bye. Bye-bye. Okay.
Stop sharing, please.